this Stoichiometry and Chemical Equations Chapter 3 video, I will teach you about percent yield. So, when running reactions in real life, we almost always isolate less product than the amount that we should calculatedly obtain. In other words, reactions are never as efficient in real life as they should be on paper. We accordingly report something called a percent yield to quickly communicate how efficient a given reaction actually is in real life. So to determine a reaction's percent yield, 1. Use the method from my earlier video, linked to in the description below, to identify the reaction's limiting reactant. Remember, everything comes from the limiting reactant. 2. From that limiting reactant and, using the method discussed in another earlier video, linked to in the description below, identify the calculated moles of the product in your question. Now, this is that product's theoretical yield. 3. Plug the actual moles of this product, which will be given to you in your problem if you're working this out on an exam or a problem set or something, or you will obtain that actual number of moles when you run this reaction in real life in the lab. You take that actual number of moles and plug it into this equation. Percent yield is actual divided by theoretical times 100. Now, the best way for me to really teach you this in practice is to do an example. So when benzene, which has this formula, reacts with bromine, which has this formula, bromobenzene is obtained according to this equation. So here's our question. When 30 grams of benzene reacts with 65 grams of bromine, what's the theoretical yield of bromobenzene? And separately, if the actual yield of bromobenzene is 42.3 grams, in other words, you run this reaction in the lab and get only 42.3 grams of bromobenzene, then what is your percent yield? Now, if you want, you're welcome to try this on your own first, then hit play, and I'll show you how to do it on the board.
Mathematically, percent yield, which I've written here as percent y, is equal to the actual product amount divided by the theoretical product amount times 100. Now, where do you get these amounts? Well, the actual product amount is given to you in the problem. It's the amount of product that the problem or question tells you that you got, or if you're working in the lab, it's the actual amount that you did get when you ran the reaction. The theoretical product is all calculated from your limiting reactant. So one of the keys then in working out a percent yield question is identifying that limiting reactant. And how do we do that? We do that using principles I talked about in an earlier video, linked to floating over my head or in the description below, using the mnemonic that I invented called BCD. B stands for balance the equation. So we're going to begin by doing that, taking the chemical equation provided and balancing it. You'll notice as you look at it carefully that it is balanced. So we're done with step B. Step C is convert everything to moles. It's given to us in grams, so let's go ahead and do that. We're going to write out the molecular weight here of benzene. 30 grams benzene here will cancel out the units down here, grams benzene. Now, if you figure out the molecular weight right here, you'll notice each carbon weighs 12. There's 6 carbons. Each hydrogen weighs 1. There's 6 hydrogens. That all adds up in toto to 78 grams of benzene for 1 mole benzene. Punching and crunching in your calculator, we end up determining that 30 grams benzene is the same thing as 0.385 moles of benzene. So I'm going to replace this 30 grams here with that number of moles. Now we'll do the same thing with our bromine Br2. 65 grams bromine, because the atomic mass of bromine on the periodic table is about 80, and each bromine Br2 molecule has 2 such bromines, the total molecular weight, or MW, also called formula weight for bromine, is 2 times 80, which is 160. Units cancel each other out, grams bromine, grams bromine. I end up with an answer of 65 divided by 160. Plug and chug on your calculator, and this comes to 0.406 moles of bromine. So I'm going to replace my 65 grams here with that number. We're now done with step C, converting everything to moles. Now we go to step D. Divide your moles by their corresponding coefficients. So in other words, here I've got 0.385 moles of benzene. What coefficient is in front of the benzene? Yeah, it's a 1, so I'll divide it by 1, and I get 0.385. And for the bromine, what coefficient is next to it? Yeah, also there's no number written, so it's an implied or understood 1. So I take 0.406 and divide it by 1, and I get 0.406. So in this last step D, the smallest of these two answers ends up winning, making it the limiting reactant. Which one is smaller, 0.385 or 0.406? Yeah, it's a 0.385. So this benzene is the limiting reactant in this scenario, and everything will be calculated from that number. The question asks us to identify the yield of bromobenzene product right there. Now, it doesn't specify the units it wants, be it grams or moles. So I'm going to just figure out what the yield in moles would be, not in grams, from my limiting reactant. We'll of course do that using dimensional analysis. Beginning with 0.385 moles of benzene, Unit-wise, I need to have moles benzene in the denominator of the next set of parentheses, and they'll cancel each other out. But what do I put in the top? Well, let me ask you, can moles of one thing and moles of another thing touch? In other words, can I put moles of two different things in the same set of parentheses? The answer is yes. But what numbers go here? Those numbers are the coefficients in front of each of these, because those coefficients are multimole or molecule-to-molecule ratios. There's an implied 1 next to the benzene and an implied 1 next to the bromobenzene, so it's 1 to 1. Unit-wise, the moles here cancel out the moles here of benzene. I'm left with moles of bromobenzene. Multiplying this through, I of course get the same number of moles of bromobenzene. So the theoretical yield of bromobenzene that I should get from 0.385 moles of regular benzene as my limiting reactant should be 0.385 moles. That's the answer to part A. Now to part B, which tells us that we actually got 42.3 grams of bromobenzene when we ran this reaction. So 42.3 grams bromobenzene is the actual amount given in the problem. That's the numerator in this percent yield. I'll go ahead and write that down here tentatively, okay? What's the theoretical amount? Well, that is what we just calculated from our limiting reactant. That is theoretical. You'll notice that there's one problem though. My theoretical is in units of moles, bromobenzene, and my actual is in units of grams bromobenzene. That's not gonna work. We have to make sure that the units equal each other. So what I'm gonna do, because this is the way I prefer, is I'm gonna convert 42.3 grams bromobenzene into moles bromobenzene by dividing it by its molecular weight. So the molecular weight of bromobenzene comes to 157. Again, keeping in mind that each carbon weighs about 12. There's 6 carbons, each hydrogen 1. There's 5 of those, and bromine weighs about 80. You add all that together, you get 157. The units cancel each other out right here. 42.3 divided by 157 comes to 0.269 moles. That is my actual yield of bromobenzene in units of moles. So I've got my actual here and my theoretical there. All I have to do is divide the one by the other, multiply by 100. Throw this into your calculator and you end up getting an answer that's around 70%. So that is my answer for part B.